Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of high-performance computing. We'll dive into key concepts like improving the impact of OpenMP work-sharing constructs, determining overheads for short loops, serialization and false sharing. Let's get started. Slide 1. Improving the impact of open work-sharing constructs. Let's start by understanding how we can improve the efficiency and impact of open work-sharing constructs. Work-sharing constructs in Open divide large tasks among threads to execute in parallel. But if not used properly, they can lead to inefficient parallelism. 1. Use appropriate scheduling. Open provides static, dynamic, and guided scheduling to assign work among threads. Choosing the right scheduling can help balance the workload efficiently. For example, dynamic scheduling is good when workload varies. 2. Chunk size tuning. Adjusting the chunk size, which is the number of loop iterations assigned to each thread at a time, can greatly affect performance. Small chunks balance the load but increase overhead, while large chunks may create imbalance. 3. Minimize synchronization. Too many critical sections or barriers force threads to wait, reducing parallel efficiency. We should minimize them where possible. 4. Reduce nested parallelism. Creating threads inside threads. Nested parallelism should be avoided unless necessary because it adds extra management overhead. 5. Parallelize large loops only. Small loops often don't benefit from parallelism because thread management overhead exceeds the gains from parallel execution. 6. Place parallel regions outside loops. To prevent repeated creation and destruction of threads, we should place the parallel region outside the loop, if the loop runs many times. 7. Combine independent loops. If we have multiple small loops, combining them into one larger loop can provide a bigger chunk of parallel work, making threads more useful. 8. Use collapse clause for nested loops. This combines multiple nested loops into one large iteration space, improving parallelism in nested loops. 9. Correct private, shared data scoping. Properly defining which variables are private, each thread has its own copy, and which are shared, accessible to all, avoids data races and improves safety and speed. Example, summing elements of an array efficiently using pragma omp parallel for reduction, plus, sum, so all threads contribute to sum simultaneously. Slide 2. Determining overheads for short loops in Open. Now, let's understand why parallelizing short loops may not always be beneficial. Short loops complete quickly, and parallelizing them sometimes adds more overhead than actual work, making them slower. 1. Thread creation cost. Spawning threads has a cost. For very small loops, this overhead can exceed the work done in the loop. 2. Synchronization delay. After the parallel loop, threads often need to synchronize, and the synchronization takes time. 3. Cache misses. Parallel threads accessing non-local data can cause frequent cache misses, slowing down execution. 4. False sharing. When threads write to adjacent memory locations, they may slow down due to cache coherence traffic. We will study this in detail. 5. Load imbalance. If loop iterations don't divide evenly among threads, some threads finish early and stay idle while others keep working. 6. Task switching overhead. The processor spends time switching between threads, wasting cycles. 7. Data locality issues. Threads accessing data located far from each other in memory makes access slower. 8. Thread startup latency. Setting up threads takes time, and for short loops, this time dominates. 9. Resource contention. All threads fighting for CPU and memory resources can cause delays. Example, parallelizing a loop with just 5-10 iterations may result in slower execution because thread management will consume more time than the actual loop. Slide 3. Serialization in Open. Let's now discuss serialization, which occurs when parallel code ends up executing sequentially, often because of poor coding practices. Serialization prevents threads from working simultaneously, limiting performance. 1. Excessive use of critical, atomic. Overuse of pragma-omp critical or atomic operations makes threads wait for each other unnecessarily. 2. Improper variable scoping. If variables are wrongly marked shared when they should be private, threads may wait to access them. 3. Unbalanced work division. If one thread gets most of the work, others finish early and wait, causing inefficiency. 4. Sequential code inside parallel regions. If code inside pragma-omp parallel isn't parallel, all threads do the same thing. 5. Thread waiting on locks. Using locks, _omp _lock _t too much forces threads to wait their turn. 6. Too many barriers. Frequent synchronization points stop threads from progressing. 7. Lack of task decomposition. Not breaking work into independent tasks means fewer things for threads to do. 8. Thread contention for I/O. If all threads try to write to a file at the same time, they end up waiting. 9. False sharing impact. Memory-related delays can force threads to slow down, similar to serialization. Example: if all threads are inside a pragma-omp critical block to update the same variable, only one thread can proceed at a time, serializing the work. Slide 4. False sharing in Open. Now, an important hardware-level performance issue: false sharing. False sharing happens when threads modify variables that are close together in memory, same cache line, causing cache coherence traffic and delays. 1. Occurs at cache line level. Cache line is a block of memory, usually 64 bytes, shared by cores. 2. Causes cache coherence traffic. Multiple cores try to keep their cached data consistent, causing constant updates. 3. Reduces parallel performance. Threads spend more time managing cache than doing work. 4. Threads writing adjacent array elements, a common mistake that causes false sharing. 5. Fix by padding, alignment, adding space, padding, between variables to avoid sharing cache lines. 6. Hard to detect without profiling tools, need software tools to observe this problem. 7. Big performance impact in loops. Loops updating arrays are especially vulnerable. 8. Worse in multi-core systems. Systems with shared caches suffer more. 9. Important for high-performance code. Avoiding false sharing is essential in optimized parallel programs. Example: if thread 1 updates A0 and thread 2 updates A1, both may be in the same cache line, causing interference. Slide 5. Advantages and disadvantages of open work sharing constructs. Advantages: 1. Easy to parallelize loops using simple directives. 2. Distributes work effectively among threads. 3. Handles threads automatically, programmer doesn't need to manage them. 4. Reduces code complexity with neat parallel syntax. 5. Built-in support for reductions and synchronization. 6. Scales well on multi-core CPUs. 7. Flexible scheduling, static, dynamic, guided. 8. Standardized and portable across platforms. 9. Improves performance for large data tasks. Disadvantages: 1. High overhead for small tasks, may slow down execution. 2. Risk of false sharing if data isn't aligned properly. 3. Limited to shared memory architectures. 4. Needs careful tuning of schedules and scoping. 5. Debugging parallel bugs like data races can be hard. 6. Synchronization delays due to barriers or critical sections. 7. Complex to manage for irregular task structures. 8. Possible contention when multiple threads access shared resources. 9. Speedup is not always proportional to the number of threads. Slide 6. Difference between serialization and false sharing. Serialization is when parallel code is forced to execute one thread at a time, often because of unnecessary synchronization. False sharing is when multiple threads update variables that share a cache line, causing cache-level delays. Serialization usually comes from too many critical sections or barriers, whereas false sharing comes from bad memory layout. In serialization, threads wait because of program logic. In false sharing, threads wait because of hardware-level cache conflicts. Serialization is easier to detect, threads visibly waiting. False sharing is harder to notice without profiling tools. Fixing serialization needs reducing synchronization. Fixing false sharing needs aligning or padding variables. Serialization slows code because of thread waiting. False sharing slows code because of constant cache updates. Both reduce the benefits of parallel programming and need careful attention in HPC.